All right, so let's jump right in with something that sounds pretty basic. Um, how long is the coastline of Britain? You'd think, like, you could just look it up,
Yeah.
right?
Oh, that's where things get a little more complicated than you might expect.
Yeah, way more complicated. Turns out that question is surprisingly tricky to answer. And it kind of takes us into this whole fascinating area called the Coastline Paradox.
It really makes you think about how we measure things.
Hmm.
Like we see a coastline as this fixed, geographical feature.
Mm,
But when we try to measure it, it becomes a whole lot more difficult to pin down an exact number.
exactly. And that's what we're diving into today, the Coastline Paradox, what it means, how it works, and what it kind of tells us about how we see and measure the world. And the stuff you sent me was, it was super interesting, this whole idea of how we measure things. So how about we unpack what makes this paradox so weird and counterintuitive? And it all starts with two main thinkers.
Yeah, it really does make you wonder, like, why is measuring something like a coastline so ambiguous? And that takes us back to this mathematician, Louis Fry Richardson, back in the 1950s. And then later, Benoit Mandelbrot in the 60s, who really kind of brought this whole idea into focus.
Okay, so Richardson. He wasn't even trying to measure coastlines, right? He was actually studying like the lengths of borders between countries, as part of his research on the causes of conflict. And he noticed something really odd. Different sources were giving wildly different lengths for the exact same border, the same coastline.
Which is kind of a problem, right? If you can't even agree on something as basic as the length of a border, how are you supposed to, like, build any solid research on top of that?
Totally. And so this discrepancy, this inconsistency, that's what made him dig deeper. And he realized something pretty important. And when you think about it, it makes sense. The shorter your measuring tool, the longer the coastline looks.
Yeah, just picture it, right? If you've got a really squiggly line on a piece of paper and you use a big, long ruler, you're going to miss all the little wiggles and just measure straight across them. But if you use a tiny ruler and really follow every single curve and turn, that total length you measure is going to be way bigger.
Perfect analogy. And that's exactly what Richardson demonstrated. If you measure a coastline with, say, a 100-kilometer ruler on a map, you're going to get a much shorter length than if you used a 50-kilometer ruler, because that smaller ruler can fit into all these little bays and inlets that the bigger one just completely ignores.
And the cool thing is he didn't just notice this, he actually came up with a mathematical way to describe it.
He did. It's that formula, right? LG is proportional to G raised to the power of 1 minus D.
Exactly.
Okay, so break that down for us.
Sure. So LG, that's the length you measure, right? And G is the size of your measuring tool, the scale. But the really interesting part is that D. Richardson found that this D value, it's like a constant specific to each coastline.
Huh. So is that like where the idea of fractal dimension comes in?
You got it. Richardson wasn't calling it that at the time, but looking back, he was essentially identifying this early version of the idea of fractal dimension. Basically, it's a way to quantify how irregular a coastline is.
Wow. So he was kind of laying the groundwork for something much bigger. And this is where Benoit Mandelbrot enters the picture, right?
Exactly. So in the 1960s, Mandelbrot came across Richardson's work, and he just took it and ran with it. He's the one who officially gave this whole puzzle the name Coastline Paradox.
Okay. And he also introduced this really cool visual idea, self-similarity. What does that mean when we're talking about coastlines?
Okay, so imagine you zoom in on a small part of a coastline. Self-similarity means that this little zoomed-in section will look really similar to the shape of the whole coastline.
So like a big bay might have smaller bays coming off of it, and then those smaller bays have even tinier inlets.
Yeah, exactly. Like those Russian nesting dolls, Each one is a smaller version of the one before it. That's self-similarity. And this repeating pattern of detail at different scales, that's a big part of why the measured length just keeps getting bigger the smaller your measuring tool gets. You just keep finding new details that you missed with the bigger tools.
And this is what led Mandelbrot to the idea of fractal dimension, right?
Right. We normally think of dimensions as whole numbers, 1, 2, 3. A line is one-dimensional, a flat surface is two-dimensional, but coastlines, there's something else.
They're somewhere in between, right?
Yeah. Fractal dimensions, they could be fractions. So a smooth line has a dimension of exactly 1, a flat surface is 2, but a wiggly, complex shape like a coastline, that's going to have a dimension somewhere between 1 and 2. And Mandelbrot actually calculated the fractal dimension for the coastline of Britain. It's about 1.25.
Okay, so what does that number 1.25 actually tell us about the British coastline?
Well, it tells us how much more detail you find as you zoom in closer. So 1.25 means there's a good amount of complexity there. It's way more winding and intricate than something with a dimension closer to 1, which would be much smoother.
So let's actually imagine trying to measure a coastline, like step by step. If we start with a really big measuring tool, let's say 100 kilometers, we're basically just drawing straight lines between points that are 100 kilometers apart. We're going to miss a lot of the curves and little details.
For sure. But then if we switch to a smaller tool, maybe 10 kilometers, we can follow the coastline much more closely. We can go into the bigger bays around the headlands, so our total length will be longer.
And then even smaller, like 1 kilometer. Now we can get into the tiny bays around individual rocks, and the length just keeps growing.
And that's the heart of the paradox. If you could keep using smaller and smaller measuring tools down to the size of, like, molecules or even atoms, the length of the coastline would just keep increasing theoretically forever because you'd be measuring around every single tiny bump and crevice.
Whoa, that's kind of mind-blowing. So it means there's no one correct answer to how long the coastline of Britain is?
Right. It all depends on how closely you're looking, the scale of your measurement.
Which is a problem, right? Like for maps and geographical data.
Yeah, it is. If someone just gives you a number for a coastline's length without saying how they measured it, that number is practically useless because it doesn't give you the full picture.
Right, like a map of the entire world isn't going to show every little detail of every coastline, but a map for, like, sailors, that needs to be super accurate. They both show the coastline, but at totally different levels of detail, so the lengths are going to be different.
Exactly. And this isn't just a problem with coastlines. Mandelbrot realized that this whole thing where complexity changes depending on how closely you look, it's everywhere in nature.
And that's where fractals come in.
Exactly. Coastlines are just one example of a fractal. These shapes have that self-similarity we were talking about. The small parts look like the whole, and they have those fractional dimensions.
So once you start to understand this idea of fractals, you see them everywhere.
Oh, absolutely.
Trees, mountains, clouds, even our blood vessels.
It's like nature figured out how to make super complex shapes by just using these simple repeating patterns. And fractal dimension, that gives us a way to describe how rough or detailed these shapes are.
So like a smooth line, that's a fractal dimension of one. But something like the coastline of Norway with all those fjords, those super narrow inlets, that has a much higher fractal dimension.
It's around 1.52 for Norway,
Right.
way higher than Britain's 1.25. That just shows you how much more complex it is. And then you have something like the border between Portugal and Spain, which is pretty smooth, that has a fractal dimension closer to 1.1 sphere.
So that fractal dimension number, it's telling us something fundamental about the shape itself, about how much hidden detail it has when you zoom in closer and closer.
Exactly. And it's not just some abstract math thing. This whole idea of fractal geometry has turned out to be super useful in tons of different fields, stuff you wouldn't even think of.
I know, right? It's crazy where this idea pops up. Like in computer graphics, they use fractal principles to create realistic-looking landscapes. You know, mountains, trees, clouds, all that stuff. And the algorithms can make incredibly detailed images from just a few simple math rules.
Which is pretty amazing, right? You get these complex visuals so efficiently, all thanks to self-similarity.
Yeah, it's really cool. And it's not just about making pretty pictures. In network theory, they use fractals to understand how information flows through complex networks, like the internet or social media.
If you think about it, the way those networks branch out in these irregular ways, it makes sense to analyze them using fractals.
Then you have like finance. They use fractal models to try to understand the stock market, which, let's face it, can seem pretty random sometimes. And in medicine, they're using fractal analysis to study tumors, to look for patterns that might help with early detection.
And even in ecology, you can use fractals to analyze habitats. Like, how complex is a particular habitat? How many different species can it support? Fractal dimension can give you insights into that.
So it really highlights how this whole thing that started with a question about a coastline has led to all these practical applications in all these different fields.
But I think beyond all the practical stuff, there's also this deeper, more philosophical side to the coastline paradox, don't you think?
Totally. It makes you question some pretty basic assumptions about how we measure and understand the world.
For sure.
Yeah.
It's like, are we ever really capturing the true length or shape of anything in nature?
Mm.
Or are all our measurements just approximations,
Mhm.
limited by our tools and our own perspective?
That's a pretty humbling thought. Like, the more closely we look at nature, the more complex it gets.
Exactly. Something can look totally simple from a distance,
Mhm.
but then you zoom in And there's this whole world of detail that you never even knew was there.
And that reminds us that our models of the world are just that, models. They're helpful for sure, but they're not perfect representations of reality. So, to kind of sum it all up, the coastline paradox, it all started with this simple question. How long is the coastline of Britain? And it led us to this really fundamental truth about how we measure the world. We learned that the length of something like a coastline, it's not a fixed number. The more precisely you try to measure it, the longer it gets because of its fractal nature.
It's amazing how Richardson, just by kind of stumbling upon this weird thing, opened the door for Mandelbrot to develop this whole new way of looking at the world, you know? With fractal geometry, he showed us how these complex, self-similar patterns are everywhere around us.
It's like sometimes the simplest questions lead to the most profound answers.
Yeah, and it really encourages us to think differently about how we measure things, how we make sense of the world around us.
It definitely does. And it makes me wonder, like, what other things that we think have simple measurements may actually be way more complex than we realize? What if the answer depends entirely on how we choose to look at it?
That's a great question to ponder. Are there other places where we might see this kind of infinite detail if we just look a little closer?
Definitely gives us a lot to think about. Thanks for going on this deep dive with us.
Absolutely.
And to all our listeners, thanks for tuning in. Keep those questions coming, and we'll keep diving deeper.